Good morning, one and all. Welcome to this presentation of Beyond Refrigerants, what's in store after HFO and Naturals. I'm Shailen Kasera from ASHRAE chapter. I, I welcome Mr. T.L. Chen, CEO Primetech Engineers Malaysia, and as a distinguished lecturer. Today, we ASHRAE Rajasthan chapter, Western India chapter, and Mumbai chapter are jointly organizing this TL presentation. Now, I would like to read the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. ASHRAE, founded in 1894, is a global society advancing human well-being through sustainable technology for the built environment. Society and its members focus on building systems, energy efficiency, indoor air quality, refrigeration, and sustainability within the industry. Through research, standards writing, publishing, and continuing education, ASHRAE shapes tomorrow's built environment today. ASHRAE is celebrating 125 years of shaping the built environment. Become a member of ASHRAE by visiting ashrae.org/join. So this is the introduction to Mr. T.L. Chen. So T.L. Chen is CEO of Primetech Engineers, an engineering consultancy practice in Malaysia. He graduated with the first class honors in mechanical engineering from the University of Leeds, England, and has been in this building services industry for over 40 years. His project portfolio includes the Kuala Lumpur International Airport, the Kuala Lumpur Central Train Station, Convention Exhibition Center, Extreme 106, and award-winning energy efficient and green buildings. Chen has authored articles and papers on fire protection, smoke management, air conditioning, and refrigeration, CFC issues, energy issues, intelligent buildings, and sustainable buildings. He served as an expert consultant to develop the National Energy Efficiency Master Plan for Malaysia, the National Mega Science Framework Study for the energy sector, the National CFC and SCFC Phase Out Master Plan, the National CFC Phase Down Master Plan, and sat in the National Steering Committee on ODS, PI, PV, and energy. Chen has instrumental in drafting the National Uniform Building Bylaws on energy efficiency and contributed to the development of various Malaysian standards. He is renowned for his innovative and daring design work, which culminated in his award-winning design for the new Securities Commission Hotel building and the Diamond building in Malaysia. He also led the development of Malaysia's green building rating system, the GBI, in 2009. We are honored to have such a nice personality for today's webinar. Chen also served as president of the Association of Consulting Engineers Malaysia during 1999 to 2001, Institution of Fire Engineers Malaysia, ASHRAE Malaysia chapter, and Kiwani's Down Syndrome Foundation. He is also an advisor to the Malaysia Air Conditioning and Refrigeration Association since 2001 and the BA's Association of Malaysia since 2007. In recognition of his contribution to the engineering fraternity, he was honored with the ACEM Gold Medal Award in 2010. So today, Mr. T.L. Chen will talk about the Beyond refrigerant, what's in store after HFOs and Naturals. The first generation of refrigerants was all about accepting anything that works, regarding the era of natural refrigerants. The second generation addressed concern on safety, flammability, toxicity, and durability. The third generation refrigerant sought to protect our ozone layer, resulting in the demise of CFC followed by XFC. Today's fourth generation seeks to arrest global warming and inevitably completely circle back to the first generation refrigerants. So what's next after the latest emerging HFOs and naturals? Are we ready and prepared to move past the era of synthetic and naturals to the future of non-RS? Now, here are some general instructions. You participants, you can post your questions in question panel or using the question button in mobile. You can download the presentation from the handouts. This webinar will be recorded and uploaded to our YouTube channel. After the end of webinar, please fill the webinar evaluation form, and you will also get a certificate after 3 hours along with the video recording and also the webinar evaluation form. Now I request Mr. T.L. Jain to present much awaited webinar on making presenter. Yes. Over to you, sir.
Just give me a minute.
Yeah.
Okay, good afternoon, good morning. Over in Malaysia, it's afternoons, so I beg your pardon there. Let me start with the presentation. You have all, the organizer has already read the synopsis to you, so I'll just skip this and go straight to the contents. Let's start off by looking at a brief history of refrigeration and air conditioning. It's almost 2 centuries ago, 190 years ago, that Jacob Perkins introduced refrigeration. Notice the colors in black and blue. Refrigeration is more important to mankind than air conditioning, which came subsequently, because without refrigeration, we'll have to be slaughtering animals every day for food. We can't preserve them, we can't do transportation and so on. So we all started using refrigerants for refrigeration first. So in 1830s, followed by 1850s, there's already a patent for air cycle refrigeration. And we move on to ammonia, carbon dioxide, ammonia for commercial refrigeration, even sulfur dioxide. And almost a century later, we talk about hydrocarbons in refrigeration. It was not until 1922 that we talk about the advent of comfort air conditioning with Willis Carrier. And since then, we have progressed at a tremendous pace. The common refrigerants back in the 1920s, when we talk about air conditioning then, were ammonia, carbon dioxide, sulfur dioxide, hydrocarbons, methyl chloride, and water. Now, what does all this refrigerant mean to us? In fact, all these early refrigerants were the problem. They are either flammable or toxic. Before the concern on ozone depletion and global warming, the challenge to find refrigerant in the early days, that's in the 1930s, 1920s, to replace the flammable refrigerants. Obviously, a lot of accidents has happened in those days, a lot of incidents. So the challenge then was to find refrigerants that are non-flammable, good stability with low toxicity, and be able to perform where we want them, the atmospheric boiling point of 40 degrees centigrade to 0 centigrade. And we did very well then. How did we go about selecting it? And that's why I'm going to take you all to your high school days, the periodic table. Let's look at the periodic table. All these elements are very familiar to all of you. They are color-coded for a reason. Now, which of these elements can we formulate refrigerants from? Unfortunately, those in purple, they solidify at temperatures required for refrigeration, so they're eliminated. Those in blue are radioactive and very rare metals, so again, you can't use them. Those in red are known toxic compounds, including arsenic. And those in pink have boiling point too low for refrigeration. So we left with the green ones, and there are 8 of them, the 8 elements. Now, out of these 8 elements, this is where CFC refrigerants are formulated. And in 1931, we formulated the first CFC R12, an excellent refrigerant that we used to use it in cars, or our automotives, and our domestic refrigerators. A year later came R11, CFC 11, mainly for chillers and certain applications. And a few years later, a very popular HCFC 22 came about that we know of in our home air conditioning, our split units, and so on. So these refrigerants serve us very well. They were ideal. They were non-toxic. They were non-flammable. They serve us very faithfully for 50 years until we've discovered their side effect of ozone depletion. So since the Montreal Protocol, what are the potential refrigerants? I call it post the OGP and GWP era. You look at CFC, the main culprit is the chlorine element that causes the ozone issue. So we're moving onwards to the hydrogen component, hydrofluorocarbons, and that's where we start looking at global warming. So the progression in a tabulated form is CFC, the ever popular R11 and R12, followed by HCFC, the 22s and the 123s. Sorry, I lost my I lost my slides. Just give me a minute. I'm sorry, I don't know what button did I press that lost my presentation material.
If Mr. Chen can see your screen, you can go ahead.
Sorry again? No, yeah, but I lost my my own slides. So I can see my own slides right now. I don't know where I clicked wrongly. Just give me a minute. Let me just sort it out. Where did my screen go? I have no idea at all. Oh yes, now I got it back. So apologies. So from HCFC, we went on to HFCs, the popular ones are 134 and recently the 32. And now today we are going on towards HFOs, the 1, 2, 3, 4, YFs, and so on. Now, post-Montreal Protocol, when we select our refrigerants, what are the criteria we are not looking at? Fiscal considerations. We have to take care of the operating pressure and temperature, critical point, and so on. And if you go along the line, you can see fractionalization, temperature glide. I'm not sure how many of you are familiar with that. That's when the two elements are combined together, two or more elements are formulated together as a refrigerant, and they may separate at different temperatures. And then flammability, toxicity, and so on. And finally, lubrication, where our synthetic refrigerants or whatever refrigerants, we need to carry the oil that lubricates our compressors. We also need to take into account the environmental considerations because of ODP and GWP concerns. And we have to look at the atmospheric lifetime, because the shorter it is, the lesser damage to GWP and so on. And finally, we also have to take into account of efficiency today, the COP. So again, in summary, we can see the properties of the refrigerants we are looking at from 22. Now the CFC is gone. We are looking at HFCs. Now we are progressing on to even other forms of HFCs and natural refrigerants. There are always pros and cons for all these elements. And formulating refrigerants, we have to be cognizant of the refrigerant triangle, similar to a fire triangle, where it's hedged by hydrogen one corner, one apex, chlorine and fluorine on the other side. If our formulation contains more hydrogen, they are more flammable. If it's more chlorine or fluorine, long atmospheric life, which means global warming. More chlorine is also toxicity, and more fluorine, we have increasing GWP. With chlorine, we also have increasing ODP. So these are the limitations we have to look at. Having given you a broad picture of the refrigerants, let's look at where do we stand in a world scenario today. And I listed 2018 because that's when my slides was presented. But anyway, 2 years later, let's see what has changed. By 2018 and now, CFCs has been successfully phased out. We managed to phase out the worldwide scenario by 2000, latest by 2010. HCFC phase-out programs are all in various stages of progress. In European countries, they are phased out by 2015. In Asia, we are due to phase out by 2030, extended for servicing until 2040. And we also began our HFC phase down, which is interesting. Now we call it phase down. And I have a story to tell about this. By the time we started HCFC phase out at the world meeting, straight away with the multilateral funds, we are already talking about HFCs. There was already suggestion for HFC phase out. As a developing country, there's India, Malaysia, those in Asia and Africa, who we are all classified under Article 5 countries. Article 5 nations means our per capita consumption of refrigerants are limited to about 0.3, I believe, kilograms over a year per capita or something along that line. That's how we're classified. And Malaysia, being a co-leader of the Article 5 countries, we objected strongly to talk about HFC phase out because it's going to cost us a lot of progress, a lot of resources, a lot of money as well. So we are only agreeable to phase down. And fortunately, this was accepted. So today we're talking about phase down, and we are all at programs all lined up. I think by 2045, we are phased down to about a certain percentage and downwards, not totally out, because it is very damaging economically for our developing countries. Low GWP and mildly flammable HFCs and HFOs are already coming on stream. In fact, they are already on stream. What are these? For example, R32 and the 1234YF, the HFOs. Today, 2 years later, they are already in place. And HFOs are gearing up to replace the high GWP HFCs. Natural refrigerants are progressing still, but at varying pace. That was the world scenario. So what about the Malaysian scenario? And I'd like you to compare against the Indian scenario. The CFC is gone and dusted. HCFC phase-out program in place. In fact, we're doing better than what we have targeted. HFC phase-down schedule is on the way. Yes, we have already formulated it. Sorry?
Slides are not moving. Slides are not moving, I think.
The slides are not moving.
Yeah.
It is. No. This is already moved. This is Malaysia scenario now, right? This earlier on was a world scenario.
Right
okay,
now,
got it.
one table is coming.
I beg your pardon?
One table is coming, CFC. Right now, one table is coming, CFC, HCFC, HFC, and HFO.
Okay, is it moving now?
No, it is not moving.
It is not moving. I'm not too sure what happened here. Okay, on my screen it's moving. It's still not moving. Is it moving? I'm screening it now.
No, it is not moving.
So what could have happened? You're still stuck on which slide now? 20.
Same slides here. One table is there, CFC, HCFC, HFC, and HFO. Right,
Are you on the triangle now? No.
no.
What has triggered it? Was moving well. I really can't figure out what is happening.
Yes, now it is moving.
Okay, so progress.
This is the world scenario.
This is a world scenario. You got it there. So the next slide. The next slide. Now I'm not moving. I'm trying to figure out what. Okay. Now the next.
You can go ahead.
Okay, it's on now. The Malaysian scenario. Have you seen that? Are you seeing that? Are you seeing the slides? The Malaysian scenario.
No, it is not Malaysian scenario. It is the world scenario.
It's still the world scenario. Now I'm on the Malaysian scenario. Let me just move it on again. Is it on the Malaysian scenario now?
Yeah, Malaysian scenario.
Okay, I'm not sure what's happening, but okay. So in Malaysia, as I mentioned earlier on, I'm quite confident that India is along the same pace, but let me know if it's not. So HFC, CFC is gone, HCFC is in progress to be phased out, and HFC phased down is already also, the program has already been done. The natural, that's basically hydrocarbon, refrigerants are increasingly creeping on board. In fact, 2 years later now, 2020, they are around now. R32, which was first introduced in Indonesia, that in 2018 was still to make its mark, and now is abundant in Malaysia. Now all the split units, the domestic air conditioners are all R32, no more HFC 410A or 407C. That's how fast things has moved. And 134A in 2018 is still prevalent, but not 410A today. HFOs already appeared, and our tallest building in Malaysia that's currently operating, the Exchange 106, the chillers are all HFOs. So that's how we progress. Unfortunately, the 3R practice remains insignificant. The reuse, reclaim, recycle. And the last part here, hydrocarbons for domestic refrigerators are finally here. And this is where I'm particularly, emotional about it, because for a long time it never appeared. We were introduced in 2000. In 2000, we talked about hydrocarbons, refrigerant, and yet there's nothing in this part of the world. And I remember making this presentation to the local audience, and after the presentation, a particular manufacturer, an engineer from a manufacturer for a Japanese brand, came up towards me and told me that, Mr. Chen, I wish you were at our annual conference in Tokyo. I asked him what happened. He said what happened was the principal showed a refrigerator charged with hydrocarbon on the video and played it out and showed how it caught fire and exploded. I said, that's real Hollywood production. It's amazing how things have been stifled from the industry. But in 2005, when I visited Tokyo, I took the trouble to look at every refrigerator in the shops. And guess what? All of them are using hydrocarbon. What happened? And even in 2000, Malaysia was the largest producer of compressors for hydrocarbon application, and all were exported, nothing retained for the local industry. So you can see a lot of commercial obstacles being created. And I can only tell you why, because hydrocarbon is non-patentable. So you can see the reason. Now I'm going to go to the next slide. Are you able to see the slide? Has it changed?
It is again the Malaysian scenario.
Okay, still not changed. So it looks like I could keep pressing this now.
Yeah.
Okay, now yes, so it
Overview.
seems it seems I could keep moving this item up. Okay, I think I got it now. Okay, the advent of flowable refrigerants. This was the synopsis. I'm just repeating it. What happened? Okay, so right now we're in the 4th generation. Let's move on. Here I'm now my turn. I can't move it. I'm not too sure now. I can't move my slides. Okay, yes. Are you seeing the slides now?
Yeah.
Okay, I'm going to show you the refrigeration progression. I hope the slide moves. Okay, it is not moving, unfortunately. I'm going to click one at a time. There's some bugs going on. I just can't forward the slides. Okay, can you see the screen moving now? No? Are you able to see the 5th generation? Okay, I tell you what, I'll just move all those. I'll skip all the animation and then show it, then explain it because something's wrong with the screen. Okay, now can you see all of it? Okay, so let's look at the first column, 1830, the 1st generation. Remember, I'm summarizing now. The 1st generation of refrigerant lasted us 100 years. It was whatever that worked, and so you can see all the blends, natural blends, and so on. In 1930s came the 2nd generation refrigerants, where the concentration was on safety and durability. This is the era of the CFCs, followed by HCFCs and so on. And this generation lasted us the full 60 years. It served us very well until the ozone problem came along. Then the 3rd generations lasted 20 years. That's post-Montreal Protocol, where we address ozone depletion and where we phase out CFCs, now followed by HCFCs, and now we're into the era of HFCs, ammonia, and also the naturals. 2010, that's when we saw the 4th generation coming on board. And how long will it last? Anybody's guess. And this is the era where we have addressed global warming. That's where we are now also beginning to phase out the high global warming HFCs. And also we are now going back to natural refrigerants as well. So we have also see the advent of HFOs. The 5th generation, when it's going to start? Anybody want to make a guess? I can only say, before I end my presentation, I attempt my take on this. Okay, let's move on to the next slide. Again, I'm having problem trying to move the slides. My webcam has been closed.
Due to your bandwidth problem, I have closed it.
You closed it. I don't know what's happening to it. It just cannot move. You're still sorting it out? I'm not able to
You can
move the
go ahead.
slides at all. But my slides are not moving. Sorry, my slide's just not moving. I can't move it at all.
Yes.
Okay. I'm still not moving it. I'm not too sure what happened.
You can press escape.
Okay, escaped.
Yeah. Now you can move your slide. It's okay. In this way, you can present.
So to forget about the full view, use this view will do. Okay, can
Yeah.
you see all this now? Yeah, but I
Yeah.
wanted to. Okay, can you see the slides now? Okay, now that we are gone, I'm going to. Are you able to see it? Yes,
You
can
can
see
see.
it still? Okay, good. So my question here, post-Montreal Protocol back in the 1990s, did we jump out the frying pan into the fire? From CFC, we move on to HCFCs and then to HFCs. I call it the American route. Well, so European went from CFCs to HFCs. Now from HFCs, we are now moving towards HFOs. And from HFOs, these are synthetics. We will move on to another synthetic refrigerant in the future. That would be my views of it. And from HFCs, also in Europe, we are also moving towards natural refrigerants. And I predict that HFOs will also, when we discover some other side effects, will start moving to natural refrigerants as well. We could have moved from CFCs to natural refrigerants, especially, again, this is my personal opinion. Okay, my personal opinion, especially for cars, we could have replace our CFC 12 in those days straight to hydrocarbons. Unfortunately, it didn't happen. All because we are dictated by certain players for economic concerns. In fact, for all of you who are not aware, even in year 2000, in Australia, there were already 500,000 cars running on hydrocarbon refrigerant. Today, I think in 2017, the last time I checked, 1.5 million cars. But in the US, they are dictated by the US EPA, and EPA has a instruction that says that first generation conversion of cars, air conditioners, must use 134A. The first generation conversion, it means those that comes out of the factory. But the second generation conversion, you can use others. Others means you can go to the workshop and convert to even hydrocarbon. So you can see the something's wrong with those statements. If you can use hydrocarbon as second generation, why can't you use it as first generation? All these are because of economic protection. So it's most unfortunate. Now, from natural refrigerants, that's what my title of my talk talks about. We may, in future, be looking at non-refrigerants. In fact, for CFCs, we could even have gone to non-refrigerants, especially even for the home refrigerators. Again, I will elaborate as we go on. So in a nutshell, in summary, we have been going around a cycle from natural refrigerants almost 2 decades ago. We've gone to synthetic and now back to it. And the other cycle could also happen from natural refrigerants to non-refrigerants. So what are the natural refrigerants? You have hydrocarbon, you have ammonia, you have CO2, water, and air. And air refrigeration, remember, patented back in 1850s. Are applications of there are products there, but again, economy of scale and also specific applications. They have been around. And even as late as recent as 2018 August, I believe this was extracted from the ASHRAE journal, extracted from the Philippine Star. So it's a group of university undergraduates experimented with it. So it's available again, whether it will be commercialized or all. And I'm going to come back to this table. What are options available? Just look at the first column, the refrigerant. Today, we are now concerned with global warming. So from looking for refrigerants with less than 1,500 GWP, which are non-flammable, as we lower down our threshold to less than 300 GWP, we will live with mildly flammable refrigerants. And downwards to less than 150, and we go down to below 10, we'll be talking about the naturals again, and to a certain extent, certain HFOs. But what I want to highlight on this slide is the last paragraph. It says, once a refrigerant is in production and SNAP approved. What is SNAP? Significant New Alternative Product. That is definition by EPA. Even when it's approved, you have to expect 2 to 6 years for all components and equipment to be available. So you can understand it takes time. So it's a lot of investments for the hardware to catch up. So what are the non-refrigerants? Two that comes to mind today, magnetic and thermoacoustic. And magnetic is around for quite a while now. The first prototype came out in 1999. It makes use of metals such as gadolinium that when it magnetizes or demagnetizes, from one stage, it releases heat, and the other stage, it absorbs heat. Thermoacoustic refrigeration. The prototype also came out in 2004. So having given you a very wide picture of the various types of technologies that are possible, let's re-examine what has happened in the past by looking at the lifespan of each of these synthetic or otherwise refrigerants. We had CFCs, which was our very faithful servant for 50 years. Now it's ended. His CFCs is now 25 years since, and probably another 10 years to go. His HFCs, I predict another 50 years, maybe another 35 years to go. HFOs had just begun its life, so probably another 50 years. Hydrocarbon, the first time around, it served us for 100 years. Now it's reborn with more interest now. It's natural. CO2, since 2 decades ago, never really seriously take off because of the high pressure or medium pressure. Even car manufacturers like BMW or Mercedes have tried it. I think they are now going to HFOs now. Ammonia, way back when we first discovered refrigeration, now they are renewed interest. Water, its own niche market with absorption chillers. Air, with renewed interest again. Magnetic, yet to commercialize, although prototypes been around since 1999. Sound refrigeration, thermoacoustic, again yet to be commercialized. Anymore, we human beings, mankind, are very innovative. We'll come up with some more. This next table, if you look at the right-hand bottom, is by a gentleman called James Calm in 2006. Even his report then shows you what we have been going through. He looked at natural refrigerants. He looked at low GWP HFCs. Even then we talk about R32, HFEs, hydrocarbons, HEs, unsaturated olefins. So in 2006, we're talking about that. Now finally it's on board the HFOs. The HFICs, the fluorinated alcohols and ketones, and others. And his conclusion was there's really no ideal refrigerants. So back to this prediction of mine. Now I'm ready to conclude it here. By the 4th generation, I asked the question, how long we think you will last? And I've included in red. We are all also very obsessed with now, or very conscious now with energy efficiency, because that will help to reduce global warming. But unfortunately, when we talk about energy efficiency, all the products around the market are all concerned about electricity energy efficiency. Only electricity. So let's look at my prediction. I'm predicting the 5th generation will be in 2050. Why 2050? Well, I'm not around to answer you if I'm wrong. So the 5th generation will be concerned about what? Climate change. We'll be concerned with 4th generation global warming. But there are all cynics who claim that, who says that's global warming. We are also experiencing global cooling. So combine these two events is actually climate change. And what are we looking at? The refrigerants. We'll see things like HFOs, maybe some other side effects as involved. We have to face it out. Going back to the naturals, probably going to the non-refrigerants, and we'll be looking beyond energy efficiency towards exergy efficiency. What do I mean by exergy efficiency? Now we have to look at the efficiency of the fuel forms itself. Now let me just give you a very simple example. India is in the subtropical continent, climate. Okay, you don't have really required too much any heating during winter. But bear with me and visualize. If you need to do heating for your room in winter, what do we use? Very commonly, we use electric heating bars, electricity to heat up the room to 20 degrees centigrade. But this electricity we use, this electricity is capable of boiling water to 100 degrees centigrade. So this electricity is a very high exergy fuel source. We do a low efficiency requirement, 20 degrees centigrade. And electricity is produced through our power plant. And by the time we can utilize 1 watt of electricity, probably at the power plant will have produced almost 3 watts of electricity due to losses, the efficiency at the plant, and then transmission losses. How about considering heating up the room by extracting groundwater? In winter, the groundwater can be 40 degrees centigrade. Now, this groundwater, 40 degrees centigrade, we can use a heat exchanger to heat up the room to 20 degrees centigrade. There's no problem at all. So only 40 degrees to 20 degrees application, a low exergy fuel to do that. So we understand exergy. The challenge is make all these heat exchanger or water products be able to make use of this low fuel to be exergy efficient. So this is what I see in the future, which we are far behind. I mean, exergy has been talked about more than a decade ago. So we are forecasting the future trend. Synthetic refrigerants, HFCs, will be replaced by mildly flammable HFCs and HFOs or some other synthetics. Any accelerated phase out will be dictated by the chemical giants, not by government. Cars, the new cars will be expected to convert to HFOs rather than hydrocarbon or others, because again, this is dictated. Natural refrigerants, certainly European-led, and the pace has maintained, if not increased, since 1997. Ammonia chillers for high-rise and commercial buildings are already established, but there's always concern of toxicity and so on, by flammability and toxicity. But we all know if ammonia leaks, the smell is there, we run for our lives. Yet, we say that we cannot control it. Hydrocarbon air conditioners are already prevalent in Scandinavian countries. In fact, Scandinavian countries introduced HFC tax. So it's over there that you can find hydrocarbon chillers and so on already in operation. So that's how shielded some of us are throughout the world, what's happening. Hydrocarbon domestic refrigerators are now the norm in Europe. And I mentioned earlier on, in Japan, since 2005 when I visited it, all refrigerators are already on hydrocarbon. And in Malaysia in 2017, I went shopping for the first time during the holiday break and checked on all the refrigerators in the shops. 50% of them are all on hydrocarbon. Today, probably 100%. What about in India? Have you all checked? Do you realize your new refrigerators are hydrocarbon? refrigerants. And remember, I related the story about the explosion by the Japanese manufacturer to the staff on the danger of hydrocarbon. I call it Hollywood. You can imagine, you know how much charge of hydrocarbon refrigerant does a domestic refrigerator require? Only 2 lighters, your cigarette lighters, that's all. And in every kitchen in your home, all of you have at least 1 cylinder of hydrocarbon for your cooking. 1 cylinder of 14 kg hydrocarbon. Yet you're afraid of a few 100 or less 50 grams of hydrocarbon in your domestic refrigerator. Obviously, engineers, you can design to prevent all this fire from happening, even if they leak. Similarly, for a car, why aren't we able to use hydrocarbon? Our car carries a tank full of hydrocarbon or petrol, and yet we can operate safely. We self-fuel our own car, yet you're talking about hydrocarbon air conditioner, refrigerant in the car. It's going to be explosive. It's no go. So all these are very unfortunate, wrong perceptions being relayed. You know that hydrocarbon in larger molecules require only about, I think, 40% of the charge you require. So you're charging about perhaps 400 to 600 grams of hydrocarbon in your car air conditioner, whereas you're carrying 50 liters of petrol, or at least 30 liters of petrol. It's amazing. And similarly, on your home split units, how much charge is there? Even if it leaks up completely, will it reach explosive limit? You can calculate that. Even the most stringent DIN standard, if it diluted, that it cannot sparkle, it cannot be explosive. I can go on and on. So all these issues, but the message is very clear. Dictated somewhere. We know the truth. Now in Malaysia, whether we like it or not, the fire authorities realized that hydrocarbon refrigerant were being fitted into a lot of air conditioners over the years, progressively, including new hydrocarbon refrigerators all coming in. So about 2015, they gathered the industry together and said that let's make sure that this is all done properly and will not cause an accident. And that's where I was again drafted to head this committee. 15 years after I first presented to local industry about flammable refrigerants. And now we acknowledge that we have to live with it, because not only hydrocarbons, but R32 is so flammable, so are HFOs. So by 2017, we came out with this Malaysian standard to guide the whole industry, the practice when you want to retrofit, when you want to have new products using flammable refrigerants. I believe we're the first country in the world that came up with this. So we are controlling it here. Developing countries and underdeveloping countries, developed nations of Asia and Africa, where India is one among us, will have little say, and for all intents and purposes, dutifully follow the World Bank directives, so long as subsidies are given. This is unfortunate, but it's a reality. Resistance to flammable refrigerant appears to be finally receding with the newly created category of mildly flammable refrigerant. Suddenly, out of the blue, I won't say out of the blue, progressively, we introduced Class 2L refrigerants. Not because we wanted it, but because the synthetic manufacturers are ready, because they have come out with HFOs, not because of R32. R32 was formulated by an aircon manufacturer, I won't name it, and I would like to think that they came up with it because of my challenge over the years. Okay, they were mildly flammable and not accepted when they first came out. But then along came HFOs with Class 2L, A2L. So they're lucky they joined the bandwagon now they proliferated. As I explained to you, in Malaysia today, you want to buy any split units, air conditioner, it's all R32 now. That's how fast we have progressed. So you can see this table. We used to have A1, A2, A3. Now we have A2L and B2L to cater for these mildly flammable refrigerants. R&D for non-refrigerant technologies. The key for R&D, unfortunately, is dictated by the States. Perhaps China is going to take over soon, or India in the future. Then we won't be so restricted. Both government and private funding will be needed to advance on researching technologies of air, magnetic, and sound refrigeration. And you can bet your bottom dollar, yes, it's just like if you can recall all the internal combustion car engines that we know of, there are a lot of better technologies, but to prevent retooling and so on, not to disrupt the market, the big giants will come and buy out your patent rights and then freeze it, cold storage it. So this will happen. And my third bullet point, the former funding is more likely to appease the Europeans who prove that there is concern for natural climate, while the latter funding is likely to be individuals or organizations who truly believe in the cause. As for development part, there will certainly be artificial curtail as long as possible. Again, as what I related earlier on, commercial reasons. There will be no quantum leap in commercialization until the capital cost for setting up a HFC plant. Now, HFO plants are fully recovered, and each time the timeline is 20 years or more. It's not cheap to set up such a plant. I think it's in terms of US 1 billion. So it is my prediction and fervent hope that synthetic refrigerant manufacturers will invest in the development of non-refrigerant technologies as an insurance, at least, against the success of natural refrigerant, which are non-patentable and cannot be monopolized. It's similar to the fuel industry, where petroleum industries are investing in solar and so on. My concluding reminder, and this is a statement I said that I believe that instigated that particular manufacturer to come up with their own refrigerant. I asked, why let 1% dictate 99%? 20 years ago, I've been asking this. The cost of your air conditioner, what's the cost of the refrigerant? Only 1% of the total cost, yet it dictates the manufacturer's 99%. So I'm asking the aircon manufacturers, you are the 99%. You should decide your fate, what refrigerant you want to use. That's how R32 came about. And when it first came about, even though it's non-patentable, it was expensive, economy of scale. But within a very short while, a few years, everybody supported it, and now the price is affordable straight away. So yes, now taking over, it's now beginning to take over the market. I'd like to see more of this happening. My next concluding remark, not so much about refrigerant, but something that I'd like to create awareness on. We all talk about efficiency, and efficiency, we are all concentrated on chiller efficiency. Today, we're talking about chiller must not be more than 5.5 kilowatts per ton and so on. We're so obsessed with it. Yet, we do not care about the efficiency of the other air conditioning equipment, the unitary system, the package units, which are very poor efficiency. But the truth is that chillers only account for 15% of the air conditioning market. The rest are all the other products, the split units, the air-cooled package units, the water-cooled package units, the DX units. These are similar throughout the whole of Asia. I'm quite sure if you check India, it'll be the same. Southeast Asia, definitely. Middle East, yes, it's same, 15% only. So I'm trying to create that. Let's push the efficiency of the other products up. That's where we are suffering. Similarly, in Malaysia, you can see the efficiency of especially air-cooled package units. You'll be surprised in the market, the larger units are less efficient than the smaller units. It's unheard of. It's only the past 10 years since my pushing that we are now matching, but it should be much, much more efficient, the larger capacity units. Refrigerant efficiency rather than hardware efficiency will continue to rule. And that's my term. Energy efficiency instead of exergy efficiency. It's our next generation where to tackle the exergy efficiency. And I'd like to end my presentation is this slide again for us to open up our vision. Look at what happened in the past. 1970 to 2000. I haven't tracked until 2020. I started tracking this because of ozone depletion. In 1970, when we are all happily using CFCs, our best chiller was we could produce was 0.8 kilowatt per ton. When CFC was phased out, we had to live with HFCs and others, which are far less efficient. We managed to improve efficiency to 0.65 kilowatt per ton. So over a span of 20 years, we improved efficiency by 0.5 kilowatt per ton. Then we started. Since then, what have we done? Sorry, I'm talking about the CFC era. That's how we ended in the 1990s. So when we're using CFC, the best we have done for 20 years, we improved by 0.15 kilowatt per ton. When we phased off CFC and used the less efficient refrigerant, in a short period of 10 years, we also improved our efficiency by 0.1 kilowatt, 0.15 kilowatt per ton. You know, the second part is always harder to do, yet we managed it. What does it show? Our complacency. We are using less efficient chiller. Imagine today if we use CFC, a kilowatt per ton could be in the 0.3 range. That's what we engineers can do. And sometimes we tend to ignore what's easier to be done. Okay, with that, that concludes my presentation. Thank you.
Thanks, Mr. Chen. Now we can take some questions from the participants.
Okay.
Yeah, question. Can you explain about the safety issue for HC refrigerant? As we know, there are massive campaign about HC refrigerant as retrofit or for the new system.
Okay, hydrocarbon. Okay, let's look at it in perspective. We say that hydrocarbon is highly flammable. All right. Now, let's look in terms, understand chemistry. For a fire to occur, remember the triangle of fire, you must have a fuel source of certain intensity. You must have the fuel that's flammable. You must have oxygen. If any of these three items is not present, you won't get a fire. Okay, I'll go to even a further extent. You know, in the fuel storage tank in any petrochemical storage tank, the fuel tank is filled with hydrocarbons and so on. What happens if there's a leakage? How do you repair the leakage? You still send in a welder to go inside. The welder wears an oxygen mask and the welding machine to weld up the leakage in a hydrocarbon-rich environment. Because it is so rich and oversaturated with hydrocarbon, right? It cannot ignite. So this is chemistry. Understand that first. So the triangle of fire, you must have certain parts per million before it can. There's a range where it is flammable, it is explosive, it's flammable, and so on. So look it up. So now let's look at, as I explained earlier on, our house domestic residential air conditioner. Our units, say, 1 horsepower split unit. In India, in Malaysia, yes, a 1 horsepower split unit is able to air condition what sort of volume of indoor space. Now you assume that all the refrigerant leaks into that room. Will it reach the explosive or flammable ignition volume? Calculate it. You use even the DIN standard, the German standard is very stringent. It's so diluted that you cannot ignite. Okay, and that is, we're assuming all refrigerants leak into the room. You know the chances of leakage is where? Is that at the external, the condenser side. Yet we're assuming this. And there are some people who tell me, what happens? I oversize the air conditioner. I want to oversize it. So my volume is now, instead of 1 horsepower, I can air condition room. I want to put a 2 horsepower unit. And with the amount of refrigerant now exceeds the limit. And say, well, engineers, you can solve that. Now you make sure there are 2 separate refrigerant circuits, because we only one reference circuit will leak at a time. That's how things are designed. Even if you design a fire incident in a high-rise building anywhere, you only design for one fire incident at a time. Right? You don't design for multiple fires. That's arson. So it's the same thing applies. So we engineers can come up with solutions for each. I talked about cars. There are a lot of cars running on hydrocarbon. What is the issue? Again, you're assuming that hydrocarbon will leak and spark off. Right? Then you design so that where there are likely to be leakage, right, that will leak into contact points and so on that will spark a fire. Just like how the domestic refrigerator, how come it's already in the market? It's similar. What happens if refrigerant leaks within the compartment? Right? All the contacts are now sealed, flame-proof, or whatever. Okay, it can be done. There's a solution to it. Now we talk about mildly flammable refrigerant R32 HFOs. You allow for that? Yes. If you don't design for it, when they leak, they also can spark a fire. So this answer to it. So refrigerators are already in the market. So why not the rest? Scandinavian countries already have chillers running on hydrocarbon. Yes, the standard that in Malaysia that we came up with gives you, dictates to you what it should be done, how it should retrofit, and if it's a plant room, it should be ventilated, and so on. Maybe gas detector if it's a larger volume. So all this can be done. These are engineering designs and engineering solutions. I hope I've answered that.
Yeah, thanks. Next question is, can we use ASHRAE refrigerant in VRF system?
Can we use what? Again, repeat.
Hydrocarbon refrigerants in VRF systems?
In VRF system, okay, this is where VRF system, the answer currently is no, not yet. We are still researching on it. A lot of brands have already used it for split units because the volume of refrigerant is fixed. But VRF, because the amount of refrigerant is now much more, and the challenge is, yes, you may have a VRF system serving, say, 5 rooms or 10 rooms, 10 fan coil units, and you are now saying that the worst case it leaks in one room, all refrigerant leaks in one room. Now it can reach the flammable limit. Yes, that's where the problem is. So until today, no, the manufacturers are saying no. They are still studying how to overcome this problem. Okay, have I answered that again? Let's move. Next question.
Yeah. Next question, why ammonia cannot be used for large commercial institutions like airport and shopping malls?
No, it has been used during the 1990s when the concern on ODP came about. Ozone depletion came about. There were quite a number of shopping malls using ammonia chillers. The big brands were all there. They have been used. There's no issue at all. It can be used. Again, yes, what is the mitigating factor should ammonia leak? How should we contain it? And what alarm should come up? Yes, it has been used before. Okay, that's the answer. Yes, you got to mitigate the risk. There's nothing that can't be done. Okay, next question.
Yeah, I'm going to take the last question. Why the R123 was banned, although due to its physical properties, it will not reach the stratosphere ozone layer. Don't you think this doesn't make any sense?
Okay, the question of CFC R123. Very interesting question because there's only one brand who champions it. You all know that. All right, and because of that, American brand that route. Okay, European disagree. All HCFC should be under the same basket. R22, the ODP value was about 0.034. 123 was 0.0 something. Yes, very low. The question is, do you want to address ozone more important than global warming or not? You decide. Okay, and who says there's no better? Yes, at one time the argument was on the I think TEW calculation and so on. Yet those are all debated, even when you talk about HCFC phase out at the world level, UN level. And in Malaysia, as an Article 5 country, we're also debating that when the Americans wanted 1, 2, 3 to be exempted, the rest of the world refused. No, it's the same basket, it's HCFC. It's still ozone depleting, whether you like it or not. We should go for other alternatives. So the answer is there, and I will pose back another question. Why is only one manufacturer all out for 1, 2, 3, while the rest says no to it? There are other reasons for it. And that comes back to an answer which I never got since 1990. Remember 1990 when we phased out CFC and we went into R22 or even 123 chillers plus 134A chillers. And 134A didn't lift off well then because its refrigerant cost was pretty high as well, and its efficiency was not as good. Okay, 123, when it first came out, all the other manufacturers also started manufacturing chillers with 123. And later on, the accelerated results, you know, a refrigerant, you have the test, they are tested on accelerated results on their side effects, the impacts. When the accelerated results came out, although the challenge was not conclusive, you know why? Because the test came out to say that mice has tumor growth, but malignant tumor. So more tests needs to be done. And straight away, a few reputable manufacturers straight away decided no, they are moving away from 123. And the question I asked when the representatives came to see me in Malaysia, even when I said that no, I'm not in support of 123, I'm cautious about it. It's not banned, but the clients need to know the facts. And the fact that when the argument says that no, 123, there's tumor, but the tumor is malignant. Some people will argue back and say that yes, malignant, but you still want the tumor in your body, even though it's malignant. And the next thing is, I asked, US is a very litigious society. When CFC was phased out, there was a lot of conversion from CFC to HFC or CFC to 123. Now, the moment these results came out, I asked the manufacturer, give me the statistics, how many owners in US immediately converted back to other refrigerants because of these results on tumor. Give me the statistics, because I know in US there will be a lot of law cases. I never got those statistics. In any case, even the accelerated results I've been monitoring until today, I've never seen it. So that answers it all. Yet I'm saying that no, we still follow each country. Even Malaysia, 123 is not banned. We only phase out by 2030. So we still follow that. So why only saying that, yes, why not 123 can be continued? It's up to you. As long as the facts are presented accurately and correctly, there are plenty of alternatives around. So make sure the clients are aware, the owners are all aware of these facts. Okay, I hope I answered that.
Yeah, next question. Currently, we are doing plethora of research to add nanoparticles to hydrocarbon refrigerants. Is it going to help protect the environment or save energy?
Okay, when you talk about natural refrigerants, hydrocarbon, okay, and now you added in nanotechnology or maybe whatever lubricants you want. You know the advantage of hydrocarbon. Okay, apart from its disadvantage, yes, it's definitely highly flammable, no questions about it. But in terms of efficiency, it is almost equivalent to CFC's efficiency. CFC 11 is the most efficient refrigerant mankind's ever invented. CFC 12 is quite close to it. Hydrocarbon efficiency R600A is almost the same as R12. That's how efficient it can be. Okay, and when you use hydrocarbon, it's a direct drop-in. That's where I make the remark that our cars, we are all being led astray. We spend so much money converting from CFC12 to HFC134A. In that process, we got to enlarge our compressor because HFC134 is less efficient, either the compressor or the condenser. So we pay more money for that. On top of that, we had to use high-duty hydraulic hoses because the pressure is higher. And on top of that, we had to use synthetic, what do you call it, the filtration, right? Because H134A is very hygroscopic. And lubricant oil is very hygroscopic. Okay, so we use synthetic lubricants, and it's very expensive. If you use hydrocarbon, it's a direct drop-in, nothing changed. Same compressor, same hose, mineral oil can still be used. Yes, we got to tackle the flammability part, how to avoid that. But we could save a lot of resources for the planet. But we didn't because somebody else dictated this space. So now we say that, yes, is that future of hydrocarbon? You already seen my prediction. It will always be there. It's natural. It doesn't cause damage to the environment. Its GWP is less than 3, 0 ODP. Let's say it's natural. It's just that we got to tackle the flammability. And the research, yes, I encourage it. Go on, it will be there. Already refrigerators are using it. Others will come on stream as well. I hope my encouragement will be taken on. Okay, next.
Yeah, thanks, Professor Chen. I think we have covered all the questions from the participant. So I, on behalf of ASHRAE Rajasthan chapter, Western India chapter, and Mumbai chapter, extend a very sincere thanks to you, Mr. Chen, for such an informative presentation. You have told the options after the HFO natural refrigerants. You have focused upon the 5th generation, which emphasizes on climate change and exergy efficiency. This is really a new idea. I would like to thanks to all the participants who have attended this presentation and benefited. I also express my gratitude to Dr. Shishirchan Bhaguri and Mr. Sandeep Mandiratna and Madan Vora, CTTC chairs, for planning the webinar in the desired way. Last but not the least, I thank the President of all three societies, Mr. Rishabh Kasliwal, President Rajasthan Chapter, Mr. Nishant Gupta, President Western India Chapter, Mr. Mihir Singhvi, President Mumbai, for supporting us. Once again, thanks to all the participants and the speaker. Thank you, sir.
Okay, thank you very much. My pleasure, and thanks for the audience. And sorry for the disruption. Thank you.
Now ending the webinar.